So welcome, thank you for coming, and I hope that you are going to learn something fun and exciting and new. I find that, as Billy said, so many people are interested in some aspects of space, but don't really know that much about it. It's not readily available. You know, people like me who like to come out and share astronomy with the public, you know, we just don't, there's not very many of me. So it's really my passion to bring astronomy education to you. I hope you learned something tonight and enjoy yourself and are entertained and take away something you didn't know before. There. Okay, I want to talk first about the telescope, because this is how we know all of this stuff. The telescope was invented actually by Johannes Lippershey back in 1608. He made glasses. He was an optics and lens grinder. And he thought of putting a lens in a telescope and invented the first telescope. This amazing telescope could magnify things by 3 times. Pretty amazing though at the time. And it's a refracting telescope. That means it has a lens in it. The lens refracts the light that it gathers. So for the first year or so after the telescope was invented, it was mostly used on land and in sea. The sailors were thrilled to have it because they could spot things out in the sea before they could actually see them with their naked eye. But it wasn't until my hero, Galileo, turned his telescope to the night sky a year later that we started looking at the sky. Hi, Pam. So in 1609, he was the first to be credited with pointing a telescope to the sky because he was the first one to get something published, to get his research published. That image there is the frontispiece of his very first published work. And that's Galileo there pointing to one of his discoveries, which is Jupiter and the 4 Galilean satellites around it. And I don't know, maybe these are muses or his girlfriends, I'm not really sure. So he discovered the rings of Saturn. He discovered the moons of Jupiter. Now there are 30-something moons, maybe more. But there are 4 big easy ones to see in a telescope. And he discovered that they were the moons of Jupiter. This, of course, blew open the Catholic Church because it meant that the Earth was no longer the center of the universe. And in fact, Galileo actually invited the Pope to come look in his telescope, to come look at Jupiter. And the Pope said, "I dare not. I cannot change my world." And he went on to publish much of his research, uncovering all kinds of new information, and spent the last years of his life on house arrest because of his claims that the sun was not the center of the universe. So for several hundred years, telescopes continued to grow in use and in size. People were getting more creative. And in the late 19th century, these huge refracting telescopes started to get built. Again, refracting meaning with a lens. So the lenses were getting bigger. The tubes had to get longer in order to have all that light gathering capability. The lens is at the front end, and the astronomer would look at the image at the back end here. The Lick Observatory outside of San Jose, California on Mount Hamilton. I don't know if it's still a functioning observatory. I know it's still there. Is it still working? Okay, Dave's going to be my backup on a lot of stuff, I can tell you. And then the 40-inch Yerkes Observatory was built 10 years later in Wisconsin. You can see, too, that they kind of improved their photography ability. This, I imagine, oops, wait, I wasn't quite done. This group here, I gotta remember the pointer. Notice all the women in here. Notice that you don't know any of their names. There were many, many women who worked in astronomy, and they all had to publish under the men's names. Not all of them are lost to history. Henrietta Leavitt Swan, and there are others who now get their credit for their work, but a lot of women in that group. One of the interesting things about these early observatories is that, well, Chris, we know that they have these slits that open and that the dome can rotate, right, depending on where they want to look in the sky. But these 2 particular observatories Their floor rose, the entire floor rose and raised the telescope up through the slit in the dome. Pretty amazing engineering feats. So by the 19th century, things were really opening up, and we were discovering a lot of stuff in our own galaxy. But there was a lot more coming. Let's see. In the 20th century, now we started seeing mirrored telescopes built. Mirrors allowed a whole different level of light gathering, and the La Silla Observatory in Chile was built in 1964. The Keck telescopes at the top of Mauna Kea in 92 and 96. I think Nancy and Phil were there just recently, right? Is it as amazing as it looks?
Yes.
And cold, huh? It's at the top of a mountain in Hawaii, it's cold. And so these telescopes were really expanding our reach into the universe. So 400 years after Galileo turned the telescope to the sky, we started sending telescopes into space. One of the drawbacks of Earth-bound telescopes is that they have to look through Earth's atmosphere. And Earth's atmosphere is wet and wavy and causes a lot of aberration. So while we can get really good resolution on things, there's nothing like going above the atmosphere and being able to look in deep space with no interference whatsoever. And so, of course, we had the Hubble and the Webb telescopes, and this is where we're going to focus the rest of the talk, and what the telescopes themselves and what they've brought in terms of what we know now about the universe. So Edwin Hubble, we need to credit these guys. He was died in 1953. I think he's such a dashing-looking man there. He was an American astronomer. This man did some serious breakthrough astronomy discoveries. Through his discoveries, he established extragalactic astronomy, meaning outside of our galaxy. For the first time, we could see outside of the Milky Way galaxy and understand what we were looking at. And also observational cosmology, which is the idea that we can study how the universe started and how it continues to grow and change by observation, by looking at it. That's really all we can do with astronomy, is look. Can't go out and test anything. So he proved that the clouds of dust and the gas from those 19th century telescopes were not just clouds of gas and dust, they were galaxies beyond our own. That was an enormous leap in astronomy, an enormous leap in what we knew. So the Hubble Space Telescope. I know you were all alive and around and watching the news when the Hubble came out. It was a big deal. It was a breakthrough in observational astronomy. The Hubble, this is a real image, by the way, you should see that, taken by an astronaut in a space shuttle right next to it when they went up to do a repair mission, or maintenance maybe. It was launched in 1990. It's already been 34 years. And it was launched on the Space Shuttle Discovery. It is 43 and a half feet long. Like, that's actually not that big in my head. 14 feet in diameter at its widest. And it has a mirror of almost 8 feet wide, a single mirror. And the mirror is, I'm assuming, back at the back end here somewhere, because this is the light gathering end. Light goes in here, passes through, hits the mirror, and then the mirror is curved, parabolic, and it bends that light into a refined, sharp image, and then sends it back to, I don't know if it gets refined in the telescope or back on Earth. I'm not sure. It sends data, and then the astronomers go, Now, what made this so remarkable is this was the first space telescope. It was the first telescope that was above the Earth's atmosphere. So this is why it started returning images that we had never seen before. And that was quite a feat. During the Space Shuttle program, which did such remarkable things, one of the most remarkable was to launch this telescope up above Earth's atmosphere, where it continues to work today flawlessly. Its main instruments are ultraviolet, visible, and near-infrared. What does that mean? You're going to see these terms a little bit more, so I wanted to explain it to you. You know, we all know that we see visible light. Here's the electromagnetic spectrum. Gamma rays, very high energy, radio waves, really big giant things that are passing through this building right now. And visible light happens to be right in the middle. Our eyes developed the ability to see visible light. On the lower end, the larger waves, right next to visible light, is the infrared spectrum. A lot of animals and bugs can see infrared. We can see infrared with equipment, with special equipment. On the other side, toward the higher energy, are the ultraviolet rays. Also, bugs can see, and fish maybe? Can fish see ultraviolet? They have those ultraviolet colors. These are my mermaids here. So we're going to go back to that. I just wanted to tell you about the infrared in particular is a little lower energy than our visible light, which is only this much of the entire spectrum. So the instruments are the ultraviolet instrument. There's that has a visible light instrument, and it has a near infrared, meaning near to the visible light. Hello, come on in. So James Webb, you know, I have to say, I have no idea why this telescope is named after James Webb. I don't think he was a very big deal. And in fact, there's a lot of kind of negative things that came out about him after the James Webb Telescope started getting a lot of publicity. But the telescope is named for him. He was an American government official. He was not an astronomer. But he was the second administrator in the new NASA organization. So that was a pretty important role. He was from Kennedy's administration through Johnson's administration. And so he saw a lot of development of the space program that eventually landed man on the moon in 1969. So, you know, he was the guy running the show. So I guess that's important.
Maybe he gave a lot of money.
He may have given a lot of money, that's true. So this is a mock-up of the mirror. We're going to talk more about this telescope because I'm telling you, in my mind, this telescope is the pinnacle of human brilliance, of the development of technology, engineering, collaborative work, worldwide teams coming together for years and years and years worked on this telescope. So it launched just a couple years ago, December 25th, 2021. It orbits the sun, 1 million miles away. Hubble orbits the Earth. James Webb got sent out to the sun where it orbits and images from orbiting the sun. If your mind is not already blown yet, I'm going to stop here because that just boggles my mind and sends data back all day long. Oh, look at this picture. Look at this picture. Just amazing. This primary mirror is 21 feet in diameter. Gold-coated beryllium. I can't see this word without thinking of that movie. Who knows the movie I'm talking about? Galaxy Quest, the beryllium balls. Surely you saw that movie. The mirror is actually comprises 18 segments, hexagonal segments. Each one of those segments is individually manipulated depending on where the focus needs to be on the image that it's looking at. From Earth, you know, like every one of those. And so hence its really amazing capability to get these really sharp images. So they're mostly in the infrared. Now that's kind of weird in our brains because we only see invisible light. So if these images it's collecting is in infrared, how do we see them? Well, they are, you know, manipulated and colored and layered and layered and layered and layered. And the people who process these images, the end result is the images we see as visible images. We're going to come back to the Webb. Here, oh, I guess we're not leaving it yet. This is a full-scale model at Goddard Space Flight Center. I imagine this is a team of people only at Goddard. because the teams of astronomers and engineers all over the world worked on this. This has been an incredible collaboration. So we're going to see what that actually does. But the scale, look at how big that thing is. So this is a little video. It's kind of quick, but how does that thing get up there and unfold? This is a little, it unfolded over 2 weeks. It took 2 weeks to unfold. So here's 30 minutes after launch. 2 hours after launch, this little foot thing comes down. 3 days later, all being run by Earth, every astronomer on the planet holding their breath for every operation.
How fast was it going while it was unfolding?
Well, it took 2 weeks, so probably not very fast. And there was big.
No, I mean like its actual speed through space.
Oh, well, the general speed out there in space is 70,000 miles per hour. Is that probably about right, Dave? I mean, things orbit the Earth at 70,000.
2 weeks.
Well, no, but I don't know that did it get there? Yeah.
I think so.
It got launched by rocket. So, but in orbit, things generally orbit.
No wonder they were going so slow on the opening.
Right? 70,000. Well, of course, it doesn't experience it because there's no gravity from which to feel speed.
From air either.
Say what?
No resistance from air.
Yeah, there's no resistance.
There's no
So
drag.
11 days, it deploys and now look, the rest of the mirrors. This is where the astronomers were really holding their breath, and the engineers. Like this, if this went wrong, it was just over.
So
And
this was-
everything went perfectly.
This is billions of dollars of
Oh,
research and
No
development,
doubt,
right?
no doubt. Billions,
So
yeah.
if anything failed, it was a failure.
That's right, and it's a million miles away, so can't send an astronaut just to go fix it like we
Yeah.
did Hubble, yeah. So, amazing feat of engineering. Now let's look at some of the pretty pictures that these telescopes bring back. We're going to go back to the telescopes in a little bit, but I want to show you some of the pretty pictures. These next few pictures are from Hubble. Hubble started just opening up the universe in whole new ways. The Great Orion Nebula is a really popular amateur astronomy telescope object, very, very easily spotted in a relatively small telescope in your backyard. The colors are a false image, so you would never, although at Oregon Star Party I saw green one year. I saw some green in there, but generally the images you see are colored. Your eye can't perceive the color if you're looking in a telescope. I'm going to show you some images by distance. So this image is about 1,500 light years away in the constellation of Orion. I put the constellation up here because many of you know Orion. It's one of the most well-known constellations in the winter sky. Here's his belt. Here's his shoulders, Betelgeuse and Bellatrix. His knees, Star with No Name and Rigel. And off of the belt, maybe I should use this, off of the belt hangs his sword. And in that sword lies the Great Orion Nebula. So the next time you see Orion and you notice a little fuzzy thing hanging down off of his belt, you are seeing the Orion Nebula with your naked eye. Pair of binoculars, and you'll be able to start to see some shape. Pretty cool. So I want to talk about this star for just a minute because we're going to talk more about what it represents. Betelgeuse. Not only a good movie, but it's of great interest to astronomers because Betelgeuse is a super red giant. It has been showing signs of going supernova relatively soon, possibly in our lifetimes. What does that mean? Stars die many kinds of deaths. I'm going to give you a little stellar evolution lesson right here. They die many kinds of deaths depending on the size they are when they're born. A star of a certain mass or amount of matter in it, when at its birth, can end its life as a supernova. So what happens is when a star is being formed, there's all this gas and dust. I should say, this is a stellar nursery. Stars are being formed right in here. There's a little area in there that may not be resolved here called trapezium that are some brand new stars. and stars are continuing to be born in that area. That is what's lighting up and glowing and heating and exciting all of this hydrogen and helium that you see in the surrounding area. So when clumps of gas come together and start to pull towards each other by gravity, something will create a little gravitational clump. And as that gravitational clump gets bigger, it starts to pull in more and more of the gas and dust around it. Well, mostly gas, not dust. Excuse me. So once that mass has enough matter in it to start compressing and spinning, this is going to be super simplistic, it starts to spin, and the gravitational pull inward starts to, continues to grab in matter, but at the same time, pressure outward is starting to fight that inner gravity. Sorry, I am going to need another drink of water here. This is stuff I love. Once that protostar has enough mass, and it's a spinning ball, and it's gotten a pretty good size, once it gets to a certain mass, all of that gravitational pressure is pushing inward, and at some point, nuclear fusion is begun at the very core of the star. All of that gravity starts to push the atoms, the hydrogen and helium atoms, together and fuse them, hence the nuclear fusion. When that fusion happens, electrons are shot outward. There's extra electrons, and those get shot out of the core of the star. So while this gravitational pressure is pulling in, these electrons start pushing out. And the star can be sort of unstable. Things are pulling in and things are pushing out. But eventually, the star reaches what's called hydrostatic equilibrium, where everything becomes in balance. So the pressure in, the gravitational pull in, and the pressure out become equal. Now it's a full-blown star, and it's going to sit there for millions or billions of years. Depending on how much mass that star has, if the star ends in a supernova, what happens is eventually the energy, the matter at the core of the star starts to run out. It starts to run out of fuel. And so when that happens, that equilibrium starts to change, and it can start to pull inward, and then that inward pressure stops, and the pressure outward starts going, and it starts actually fluctuating in and out until it becomes, pretty unstable. At some point, that star immediately and instantaneously collapses in on itself, and then instantaneously blows everything out into space in the most cataclysmic event that we know of, not aside from anything. The most cataclysmic event that we know of. And in that supernova, in that explosion, all of the matter in the star is blown out into the universe, into the space around it. And in that time, in that moment, in the moment of collapse, all of these different atoms are shoved together and made into new atoms that are all heavier than lead. Gold and silver and platinum and all of the heavy elements are made in this supernova collapse and then burst out into space. And that is the only way those elements are made, is in supernova explosions. That's it. That's all we get. Of course, you know that we have these elements in our bodies. We have gold and we have platinum in our bodies. We have these elements in our bodies, let alone Earth. And so it really is true that we are made of stardust. From a supernova. That just is mind-boggling. So we're going to go back to supernovas, or we're going to go back to remnants of supernovas. Let's see.
And Beetlejuice.
Not Betelgeuse, that was it. Bye-bye, Betelgeuse. We're just going to have to watch it go supernova. This is the Ring Nebula, M57. This is called a planetary nebula, but it has nothing to do with planets. This is one of the objects that early astronomers thought sort of looked planet-like. They could see it was a DFO, a dim fuzzy object. And because it was round, they thought it kind of looked like maybe it was a planet that they couldn't resolve. What this is actually is another way that stars die. So this particular planetary nebula is 2,000 light years away up in Lyra, which is going to be up all summer long, almost straight ahead, straight overhead. So this star has died a very different death. This star didn't have enough mass, or didn't have the right mass to go supernova. So what this star did is, as its fuel ran down in its core, that grip, that gravitational pull started loosening its grip. And that outward pressure of the electrons going outward started to take over. And so some planetary nebulas die a very quiet death. That release of the envelopes of gas, a star is kind of like layers of different elements. They're like an onion. So the outer layers start to drift away from the core of the star, and this is the end result. What it leaves, dead center, is a white dwarf. That is the core of the original star. White dwarfs tend to be around Earth-sized. This used to be star-sized. So this white dwarf, it's very, very hot, but it's not, there's no more nuclear fusion happening. It's just going to radiate. It's so dense that it's going to radiate heat for millions of years before it becomes maybe a red dwarf and then just a little coal. But it gives these beautiful images of this basically dead star. And this material will continue to drift outward into space and become fuel for new stars. The Cat's Eye Nebula. This is one of my favorite telescope objects. It's hard to find and always very satisfying when I do. This is also a planetary nebula, but quite a different image of one. We can see the white dwarf in the center there, but we see these layers in a very different way that we saw the Ring Nebula. So what's going on there? Well, this one is about 3,300 light years in distant, and it's in the constellation of Draco in the north, Draco the dragon. And it is, so these circles that we see, for all the way out here as well as these, are this particular nebula is not just kind of letting go of its outer envelope like we saw in the Ring Nebula. This one, astronomers have found, are actually pulsing its layers off every 1,500 years or so. And so that's the result of what we're seeing here, is just every 1,500 years it kind of went, there goes some more, there goes some more, leaving the white dwarf at the center. This is mind-blowing to me. Every shell, all of these shells that we're seeing, contains as much mass as all of the planets in our solar system combined. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Neptune, Uranus, Pluto. Put them all together, and that's the mass of one of these rings. So stars have a lot of material in them. So this particular image I've seen described as like seeing an onion cut in half. Because of the way the telescope is imaging, we're actually seeing through. I mean, obviously it's round, right? It's not nicely cut in half like this. It looks like this all the way around. But the way telescopes image, we're able to so this circle here is probably, like way out here. So we're looking down into this sphere of layers.
So as the star is moving through the galaxy, is it still in the center of those orbs, or is it out ahead of it?
The stars don't experience their movement. Everything in the universe is moving, and it doesn't experience any movement. There's no wind.
Well, I'm thinking like you know how they show those images of our planets kind of corkscrewing behind and around.
Yeah, that's I know what you're talking about. That falls into cosmology and the way the universe all moves.
Okay.
So these are moving, but we don't experience it, they don't experience it in the big picture, and that's,
So it is kind of in the center then
Of-
of the orb.
the star is. The
Yeah.
white dwarf is still in the center. It's surrounded by concentric rings. But just the image we're seeing different levels of the rings. Does that make sense? Uh-huh.
Yeah.
Peggy?
It says 1,500-year intervals. How do we ever figure that out?
Astronomers have done just the most amazing brains. Everything we know is based on what we see. And we know a lot about stars. We know by their spectrometry, by what the light, when we receive the light from a star, an image like this, we can actually tell what the elements are that it's made of because of the wavelength that it's coming in. We can tell how fast it's moving away from us. We can tell how old things are. And we can, so they use these instruments to determine, like, this is moving closer to us. This is moving, at a different rate. They have their magic wand, is what my answer is. It's a lot of instrumentation that they can calculate these things. And of course, that's a roughly 1,500 years. But they can date things to a phenomenal degree. And this is pretty close. This is a close object. These are close objects. So the Crab Nebula. Isn't that a great picture? I love the Crab Nebula. This is the remnant of a supernova. Astronomers are still observing this to this day, and it was visible in the daytime sky. This is a supernova blew in 1054, 1,000 years ago. It was visible in the daytime sky for a couple of weeks. And we know this because it was well documented. It was documented by Chinese astronomers. It was documented by Puebla natives. And of course, Europe was documenting lots of this stuff. So all of a sudden, can you imagine, that you live in 1054, and all of a sudden there's a brand new daytime star. And of course, that portended all kinds of evil things, I'm sure, but not for us, because this is the end result. This Crab Nebula is about 6,500 light years away. It's in the constellation of Taurus, so more of a winter object. Also readily visible in small backyard telescopes. And it's 11 light years across. How long is 1 light year? How many miles? 9 trillion. 9 trillion miles, 1 light year. Or 10 to the 6, 3 times 10 to the 6 meters per meters, kilometers. It's big, and it's been expanding ever since it blew 1,000 years ago. In fact, we have been imaging the Crab Nebula long enough now that astronomers can actually see its growth over time, over different images. We've been able to see its expansion. It is still expanding at 930 miles per second, 1,000 years later. And it's beautiful. We're going to come back to this one with a web image. So this globular cluster, one of my very favorite objects. Globular clusters are just not like anything else. They're not fuzzy, they're not dim, they're bright and shiny, and they look like a little jewel box. I just love globular clusters. This is in the constellation Hercules, M13, up all summer. Pretty easy to, it's not easy to find always, but you can certainly spot it with a small backyard telescope. It's quite bright, maybe even binoculars, good pair of binoculars. This particular image, I think this is one of my very first telescope images when I started observing. The glob, I like the name glob, it's a glob. It's a globular cluster. This one comprises about 100,000 stars. You can see that they're gravitationally held, they're gravitationally related. There's still lots of space between them, but from our perspective, we see this incredible jewel box of stars. It's about 25,000 light years away. Now we're really pushing out there. Globular clusters tend to hang around the center of the galaxy. Our galaxy, you see this? That's our galaxy. Our galaxy is a spiral galaxy like this with a humongous black hole in the middle. And globular clusters hang out around the center, close to the center of our galaxy. So if this is our galaxy, we live in a spiral galaxy, and it's kind of oval shaped. But if you turn it on its edge, it looks like a fried egg. There's a little bulge in the center there. And we're going to see some galaxy images that you can see all kinds of different orientations. Some are like this, some are like that, some are like that, and some are full face on, like this. We'll see some more of those. And Hercules cluster is about 145 light years across. Just see, I'm just throwing that out. Times 9 trillion miles. And again, it's easily spotted in July. So this is a good summer object to get your binoculars, or if you have a small telescope or even a big telescope, like Dave does. We can all go to Dave's house. Okay. This is, I wanted to show you this image because this is from an amateur astronomer from his home-based telescope. This is what when I picture the M13, this is what I picture, because this is not far from what you'd see in a large telescope. In fact, this was from a home telescope. So you can see that the center is very dense. It's not as resolved as that Hubble image. So Hubble, getting up above the atmosphere, is able to really zoom in and resolve all those stars in the center. But one of the things I learned as I was learning how to see, because when you use a telescope, you sort of have to learn how to see in it. You have to learn how to see what you're seeing. That there's kind of little trails off. And that it's not just a clump, but there's little, oh look, a galaxy. That's a galaxy. That probably is a galaxy up there too. That's not. We're going to see more galaxies. But it's just a beautiful, beautiful image. And I love globular clusters. This is the Whirlpool Galaxy, M51. One of the probably most photographed galaxies. It very conveniently is a nice face-on spiral. So we see it face-on. We see the very bright center. We see the strong spiral arms here and the gases and dust and all that energy that's happening. And it kind of passes right in front of this little sister galaxy. Little sister, clearly. Now, we are not seeing any resolved stars. You are not seeing any stars. This is really far away, 31 million light years away. Now, you've noticed we've gone from 25,000 light years to 31 million light years. There's nothing in between. There is, once you leave our galaxy, it is space for millions of light years. There is just nothing out there that we look at. Nothing to see. So we take a big leap when we leave our galaxy, which is what we've done here. Let's see, I think I have more there. This is about 60,000 light years across. Our own Milky Way galaxy, thank you, Jordan, is about 100,000 light years across. By the way, if this were our galaxy and it's 100,000 light years across, we live about a third of the way in from the outside edge. In there, in the Sagittarius armor spur of the Orion armor spur. This object is near the end of the handle of the Big Dipper. So we all know what the Big Dipper looked like. You can picture it in your head. The very last star of the handle, it's just right there. But it's actually officially in the constellation called Canis Venatici, which you've probably never heard of because it's a really small sort of, but it has a great galaxy in it, small constellation. Oh, sorry, that was the dwarf galaxy. Is NGC 5195. In case you're wondering, these numbers, the M numbers, are catalog that the astronomer Messier, Charles Messier, started collecting when he was looking through his 19th century telescope. He started numbering objects that he could tell were not stars. He didn't know what they were, but he knew they were something. And so this was the 51st in his catalog of things that weren't stars, or comets.
Well, he was looking for comets.
He was looking for
He
comets.
labeled these because he didn't want to look at them again. Because he was looking for comets.
Yeah, and
This
of
is
course,
the catalog of what not to look at.
what not to look at, and it has turned out to be every amateur astronomer's list of what some of the first things they learned, because they're so big and easy to spot. NGC is the New Galactic Catalog, and these are more refined and harder to, they were harder to identify back then. They didn't make Messier's not look at list. So, Hubble Deep Field. One day, Hubble sent back this image. Everything you see in this image, with the exception of anything with refraction points, is a galaxy. Every dot, every mark, you can see here's a spiral. Here's a little edge on. Here's another spiral. So these are probably closer to us. Another little spiral up here. Every single light point is a galaxy with hundreds of billions of stars.
Wow.
This image, if you picked up a grain of sand and held it between your fingertips and held it at arm's length, that is how big the piece of sky is that that image came from. That image is the size of a grain of sand in the sky. 10,000 galaxies in a grain of sand, and it's like this probably in every direction. Absolutely, Googleplex number of galaxies. So when this image came back, it really opened up a whole world to astronomers now that they could start really looking at this deep sky that they had never seen before. They knew there were galaxies out there, but they were not prepared for this.
So, Jessica, so the Hubble telescope is a long ways out from our Earth that we're all riding, but it's taking photos, images that are gazillion miles out. How long does it take to transmit that information back for astronomers to do something with?
Probably a couple of light minutes.
Well, it depends on where the data rate is. I mean, you know.
Yeah, it's just above the Earth's atmosphere, so it's sending it at the speed of light. It's sending data to us at the speed of light, generally speaking. And it's not very far. So like Saturn, Jupiter is 8 light minutes away, I think. Or maybe
Light
that's the
minutes.
sun.
Okay.
So minutes. But they're sending a lot of data.
Yeah, the images are, there's a lot of data, probably gigabytes of data for
Right.
this image.
Right, and so I'm sure they collect data for days.
Wow.
Yeah, but it comes at the speed of light. the
So
data.
that could be exciting with the AI technology for computing it and turning it into images a lot quicker, maybe.
They do use it.
They do use it
Yeah,
already. I'm
it's-
sure
it's,
they were like, oh, where have you been? Yeah. Yeah, I'm sure it's used in all manner of sciences that we don't know about. It's just their daily lives. All right, so we've looked at the Hubble telescope. We're going to look at some Webb images, but I want to talk a little bit about the comparison. Now, they are not competing with each other. These guys are brothers. They are very close to each other. They don't talk to each other, but they have the same family. So the Hubble Space Telescope's, again, a single mirror and almost 8 feet in diameter. The Webb is 21 feet in diameter, and it's made of 18 different segments that can all be refined as it focuses. This one looks at visible light, hence the mirror, and the infrared. James Webb Telescope has 4 main instruments on it, near and mid-infrared, and another kind of infrared, and another thing that I didn't really understand, so I didn't put it on. Because if I don't understand it, I can't explain it very well. So the diameter, though, is what you really can appreciate here, the difference in the diameter of telescopes. So much more information gathering capabilities over here.
Can they use them in tandem, like binoculars? Kinda?
They do that with Earth-based telescopes.
Yeah.
I don't know if that's a plan for these two telescopes. I would assume not. Yeah, but I don't know. I don't know that. You may remember this image. This was the very first image Hubble sent back. Like, look, world, look what I did. And it was absolutely mind-boggling because we saw detail in the Eagle Nebula, and this little part of the Eagle Nebula that we had no idea about before. And just to give you a size of an idea of scale, there are stars being formed at the tips of these. Those are stars. Stars, little stars. So this is a little stellar manufacturing company. All of this gas and dust, probably hydrogen and helium, is just in these huge clouds waiting to be born into stars. This is visible light. This is a Webb near-infrared imaging. Now, one of the things about infrared is it can look through dust. Visible light cannot look through dust and clouds, but infrared can. Hence, you see all of that is gone. You see details in the pillars that are just black spots over here. We see so much more detail all the way around because we're looking right through all of this gas and dust that obscures so much. Notice also that we can also see all the background stars. Can't see them over here. If we see them, they're in front of that dust. So this is the change of ability to see that the Hubble has given us. It's just a whole nother level of ability to see. The Eagle Nebula is about 6,500 light years distant, so we're back in our own galaxy here. And 8 light years across. Now, I think by across they mean that way, but I don't know that for sure. So the Webb, this is a Webb image of a different ring nebula called the Southern Ring Nebula. And this is the same telescope, 2 different instruments, infrared, near infrared, and mid-infrared. So 2 slightly different neighbors on the electromagnetic spectrum. You can see that it gives us very, very different information. Most importantly, remember the thing about planetary nebulas is they have what in the center? A white dwarf. Good, yeah. But this is not that because white dwarfs don't have refraction lines like that. So what's that about? Well, in the mid-infrared, what we see is that the actual white dwarf on the left there is being obscured by this star here, which is still a star. Remember, the planetary nebula is a dead or dying star with a white dwarf at the center, but the star next to it is actually a companion. The 2 of them used to orbit each other in a binary star system. Very, very common in space, binary and multiple star systems that orbit each other. So this is still orbiting the white dwarf, but it hasn't lost any of its shell yet. It's not dying yet. It's, well, probably dying, but we don't see it yet. So, yes. And so the brighter star, again, hasn't shed its layers yet. It will. We're going to get like a double ring nebula at some point in somebody's future. So the gas in this nebula there is heated by the white dwarf. In this image, it's the blue light, and the white dwarf is energizing the gas in the red light there. Is that right? Am I saying that right? So the 2 infrared images are revealing different information. And then both stars are lighting up the outer regions here, the blue and the orange. So that's the beginning of that release of the gas around the stars.
So you said that the images are colored by somebody, that they don't come through like this.
They don't come through like this, but the information they're sending says that they're this color. Do I have that right?
Well,
Right,
they
they're-
probably use different filters.
Yeah,
And the filter will let through a certain wavelength, which would be a certain color.
right. So they filter these to be specific colors relative to what they're looking at.
I would imagine it's from the heat signatures.
Energy is probably a little bit better word, but yes. So they're not colored. Somebody doesn't decide they're going to be a certain color. The filters that are used for this particular spectra
Or affiliated with gases?
result, yes, yes, the elements, the actual elements themselves,
Yeah.
the hydrogen and helium.
So can you explain the reversing colors?
Yes, because on the first one, the white dwarf is heating up this blue. It appears blue because it's looking at near infrared. It's looking at a different wavelength. This image is we're looking at the same region but in a different wavelength. So just like your shirt is yellow and his is red because they're two different wavelengths, those areas show up as two different colors because we're seeing them in two different wavelengths on that spectrum. It gets a little twisty-minded there. Don't twist your mind. You can just look at the pretty pictures. Okay, now we're going to go back to the Crab Nebula. Remember, this was a supernova that was seen by people on Earth in 1054. And it is really, I think I said it's a really easy object to see in the winter because it's in Taurus. M1, it was Messier's first object that he said, I don't want to look at that because it's not a comet. So I wanted to show you that because this is an image from the Webb Telescope of the same image, of the same Crab Nebula. This is a combination, so telescopes do work together, of the Webb and the Chandra, which is an X-ray telescope. So it's looking at much higher wavelengths on the spectrum, way over to the left of the ultraviolet. Now, so we don't have the whole image here, but you can kind of see that it's the same shape, it's kind of that oval. But what is so spectacular here is that we see something here that looks nothing like the Crab Nebula here. Okay, so I want you to pay attention to that central area there, where the origin of the explosion was. And then this is the central area here. Wow, explosion. We see something here we have never seen before. I also want you to see the date that came out. This is a brand new image. What is that? This is a neutron star at the center. This is not a drawing or a rendition. This is a real image from telescopes. This is a neutron star here. Remember I told you that stars have different deaths, and this one is a supernova, and the white dwarf, the planetary nebula have white dwarfs in the middle. Many supernovas still leave a core behind, and they are usually, maybe always, neutron stars. Neutron stars are the biggest mind blowers next to the fact that the whole thing blows up like it does. Because a neutron star, when that collapse happens and everything gets shoved into the center, into the core of the star, all this material is blown out, but there's a little bit left in the middle that was so shoved together by the gravitational pressure of the explosion that it is the densest material known to science outside of black holes. They are generally about the size of the moon. And John Dobson, my old astronomy friend back in the day, used to say it would be like putting two giant battleships in a shopping bag. Or a teaspoon is tons and tons and tons of this material is a teaspoon. It is so dense that we don't know anything else like it other than black holes. And they're their own mystery, to me anyway. So
It almost looks like rings coming out around
Yes,
it?
we're going to get to
And
that.
like a beams coming out the end.
That's exactly right. You're exactly right. Neutron stars, one of the other amazing features is that they spin incredibly rapidly. 30 times a second. This is a moon-sized, heavy, heavy, very, very dense object spinning at 30 times per second. They are spinning so fast that they send out a beam of radiation out this way. Because we're kind of seeing an edge on here. It's almost edge on. And at every rotation, if they're oriented just right, that beam of radiation passes the Earth and we can record it on our instruments. And that's how we know how fast they're rotating.
Could it actually cook other places?
Sorry?
Could it cook other places with that radiation?
No, but the spread out matter can certainly perturb a lot of stuff around it.
Okay.
No, it pretty much just sits there and spins and sends out beams of radiation. Now, when these were first discovered, the very first neutron star discovered that was sending this beam, a woman astronomer, I wish I knew her name, I don't, but it's known, thought that it was a signal from another life form. And when they did, until they knew what it was, they actually called it LGM, little green men. So this is an LGM.
Surprising they took her serious.
Well, they didn't. They were certainly getting the signal, but they didn't know what it was, and it was so rapid. It took them some time, but they eventually discovered neutron stars. When they do this, not all neutron stars send out these beams in this pulsing way. When they do, they're known as pulsars. So it's a pulsar neutron star. So Chandra, which is a telescope I've not talked about yet, with its repeated observation, it is what started to show these concentric rings. That is the shock wave of that radiation, of the radiation that's bursting out of this neutron star. It's creating shock waves, and that is what we see here. So this is brand new information. You're probably the first people in Ashland to know, because it just came out. So this is a big leap of our information that the Webb Telescope is bringing us. You guys doing okay? Okay.
Where's Chandra?
So where is the Chandra X-ray telescope? I don't know. Do you know? Is it a space telescope?
It's
space.
like an orbit
Yeah.
similar to Hubble,
Yeah,
but not necessarily the same orbit, but it's in that general area.
yeah. So it's orbiting.
It's on the same place of James Webb.
Say it again.
It's on the same place of the James Webb.
Oh, it's around the sun? Oh,
L2.
it's an
okay.
L2?
Thank you, Phil.
Oh, okay.
It's orbiting the sun.
Oh,
So this is Stephen's quintet. I included this image just because it's different. I like it. I only have ever found it once, even though it's kind of it takes up a big area of the sky, about a third of the width of the moon. But this is a Webb Telescope image of Stephen's quintet. This is 5 galaxies in the constellation of Pegasus, so that's up in the fall. There's 1, 2, 3, 4, and 5. And these 4 are in a group. This one is actually much, much, much closer. I'll tell you how close in a minute. One of the things I want to mention is that whenever you see these images with the spikes on them, those are going to be stars. And you can think of them like stars, like raindrops on a window. You have raindrops on your window, but you're looking out the window at the mountains way, 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 way over there. That's what those stars are. They're raindrops on a window, and then we're looking across vast space, millions of light years away. And so that means that all the other dots in this image are what? Galaxies. Every image that doesn't have a spike, there's a little spiral. There's like a elliptical maybe. There's another spiral. All of these are galaxies. It just blows my mind. And then here's a real close-up star, raindrop on a window. So this is a composite by Webb's two imaging instruments, the near IR and the mid IR infrared. And so they do layer these images. Some of these images are 1,000 layers of images. I mean, they're really manipulated is not the right word, processed. They're highly processed in order to gain these images. So these images show the galaxies, these are all pretty, except for the one on the left, those are all pretty new, young stars, fresh galaxies. These are pretty bright new galaxies. There's a lot of stellar formation happening in there. And these sweeping tails of dust here, like this, and here, is because they interact gravitationally. They are near enough that they rip material from each other. You know, they are all moving, but they're not moving all in the same direction. So if they get close enough, they can literally rip material by gravity off of.
Isn't our Milky Way and the Andromeda
Close together, yeah.
Yeah, they're merging.
That's
or
our.
whatever?
Yes, they're probably heading toward each other. Yes, that's true. So one day our two galaxies, ours and the Andromeda galaxy, will collide. So if you haven't sold your house yet. So as a result of these really close together galaxies, they're kind of just smashing through, and the result of those sort of near misses is this really bright streak here of just gases and dust that are highly energized by these interactions. So just emitting a lot of light and energy. So this galaxy, it looks like it's in the same grouping, but it's not. It's actually a nearby tree. It's not quite a raindrop on a window, but it's a nearby tree. It's only 40 million light years distant. The other four are about 290 million light years distant. So, you know, you can't even come up with a number of the ones that are in the distant background. Billion
And the
light years.
light still reaches us.
Took a billion years, but yes, it did. Yep. So yes, it's pretty amazing. So I want to show you the comparison of the two instruments on the Webb telescope. This is the mid-infrared of those same galaxies, right? And look, it has wiped out all the dust. We can compare it. So it has wiped out all of the dust, and we can now see much more detail in each of these galaxies and just more information. We can see more of this streaking between the two galaxies there. We can see all kinds of activity up in here. That is a raindrop on the window, obscuring the center of that galaxy. And we can just see, this is not a spiral galaxy. It's kind of a clumpy galaxy. These look like elliptical galaxies, but again, these aren't pretty new, and so they're still forming.
What's wild is you think of the light years away, 290 million light years away. It happened 290 million years ago.
That's
so
right.
You're literally looking at the past.
Oh, absolutely, 100%. 100%. We are looking into the deep past. You bet. That's a mind boggler right there.
Yeah, in the present.
Oh, here we go. That's a slide I thought I was going to show you. It is. So this is the comparison of the two different infrared imaging instruments on the Webb. Really quite different information from each one, and both of them have a lot of information. Look at that little spiral galaxy hanging out right there. So again, just lots of information that this helps astronomers understand how galaxies are formed, how they evolve, how they interact. It just sends a lot of information back that gives astronomers a lot to study. This little elliptical galaxy is not in this picture, by the way. It's missing. I didn't take the picture, though. I would have gotten it in there. So galaxies. These are all images that the Webb telescope has taken of several galaxies in our neighborhood, I guess you could say. You can see the cores of all of them. They all, I'm sure, have massive black holes in the middle. This is a barred galaxy here. Most of them are spiral. Here's another little barred, little S-bar galaxy. That might be an elliptical galaxy. So depending on the shape of the galaxy, they're designated as different kinds of galaxies. So there's lots of pretty pictures there. Yes.
Do you happen to know how they catalog them? I mean, there's so many of them. How can they even give them a number or a name?
Well, the near ones that we study have been cataloged for a long, long time. That's NGC numbers, the New Galactic Catalog. The more distant ones, I'm sure they have some kind of designation, but they're like blah, 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 computer stuff, I'm sure. You know, they don't have like, they're not like the Lynx Nebula. So what is the future of telescopes and astronomy? As I said earlier, I think the Webb Telescope is the pinnacle of technology that we have seen in humankind. I really do, especially considering the collaborative work and the engineering and the decades. It took a couple of decades to get that telescope up, and it went flawlessly, which is just like, I don't know, they were knocking on a lot of wood. So what's coming? The Habitable Worlds Telescope, I'm sorry this is so small, but I'll let you know. This is a 6-meter telescope that will do infrared, invisible, and ultraviolet, much like the Hubble, but it is designed to explore exoplanets, planets outside of our solar system, looking for signs of habitability. Can we find another planet that is in the Goldilocks zone like we are? Our planet is in the Goldilocks zone because it's not too hot, it's not too cold, it's just right for life. It's called the Goldilocks zone. So that is exactly what this is built to look for. It will be capable of other research. The Origins Space Telescope, this is a far infrared space telescope, 5.9 meter mirror. Quick, how many feet? 18? And it is cooled, I found this fascinating, to 4.5 degrees above absolute zero. I don't know why. Anybody know why?
Less noise.
Less noise?
Colder gets, the more sensitive it gets, and there's less, it just gives a cleaner image.
Cleaner image, all right. Thank you, Dave. It is designed to study the formation of galaxies and solar systems. So these are, they have specific purposes. So this is, again, we're looking at galaxies that were fairly newly formed. That's what this telescope's specialty will be, as well as solar systems. Of course, several years ago, we found the first exoplanet, the first planet that was outside of our solar system. And that opened the door wide open, and we have hundreds and hundreds and hundreds of them now. So now, thousands, I'm sure, thousands. Once we knew what to look for and how to look, and we had the instruments, it just opened up the whole new world. So this is specifically designed to look for other solar systems I don't know if it's in other galaxies, might be in our own galaxy, I'm not sure about that. The Lynx X-ray Observatory, this is the huge X-ray space observatory. These are all going to be space observatories, so they'll all be above the Earth's atmosphere. This one is similar to the Chandra X-ray Observatory, 50 times more powerful. Oh my God, it's designed to study the formation of black holes, which is still a lot of mystery still in there, lots of room for research, and how galaxies evolve. So with the astronomy has a lot of really amazing stuff to look forward to. These are often decades in the making. You can imagine there's a lot of money, there's a lot of engineering, a lot of technology is changing so fast, even for the people building the telescopes, that it can be, things can be obsolete as soon as they're made. So, it's a real challenge to get these things done, and we do it. They're global projects. It's one of the things that brings the world together, is building these telescopes and studying the cosmos. So maybe we should all become astronomers. And yeah, I think that's it. Ooh. Thank you. I know it was easier to ask questions when a certain slide was up, but does anybody have any questions they'd like to ask now?
Are there any observatories that are visible or visitable to the public in Oregon?
There's Bend, the Sun River Observatory in Bend. Eugene Lane College has an observatory. I don't know that it's open to the public.
Pine Mountain.
Pine Mountain.
Palomar still there?
What it?
Palomar, is that still?
Palomar's in LA.
Oh, you're talking about just around?
Yeah, in Oregon. Yeah. So Bend, it's out toward Bend. The
Pine Mountain.
yeah.
Mm-hmm.
Yeah.
Is that part of the area that they designated a light sensitive sanctuary?
It could be, yeah, because that was a whole new thing. You guys saw that Eugene, Lane County is designated a dark sky site, which is incredible. I mean, that is just phenomenal. It means that all the street lights and people's house lights and porch lights are mandated to be low sodium, which means there's not a lot of light being emitted, and covered. If you have a porch light that shines in the sky, please cover it, because you are contributing to light pollution. All you need to do is build a little ledge over it so that you don't send that light up to the sky. So we can all participate in darker skies. Yes, Pamela?
So a friend asked me to ask about the comet that's coming awfully close to hitting the Earth.
Well, it's probably not going to. Dave, do you know a comet
I'm
coming?
not sure which one that is. There's several
There-
right now, but none are gonna come
Yeah,
up close. There's,
no.
when they say close, they mean like twice as far away as the moon. That's
Yeah, that's
for
close.
us.
Yeah,
So,
and not like you're gonna get a wind on your cheek.
But even when it's coming back in like 7 or 8 years.
well, yeah, they constantly calculate the orbits, and there was one that was possibly going to be really close, but the more calculations they did, they figured it's not going to be as close as they thought.
And we did just have a couple comets come through.
Yeah, there's
Just
two.
recently.
There's two in the sky right now.
Two
that
in the sky
are
right now.
visible,
Yeah,
you know.
yeah. Any other questions? Yeah, Bill?
You mentioned that black holes are still a mystery, but is there something out there that is beyond human comprehension?
Yeah, a lot.
Most of it.
Uh,
Dark matter?
When you talk about it.
Yeah, I'm thinking of that.
Whew, that was close.
Dark matter seems to be one of
Yes,
And
yes,
dark
that's
energy.
right. The 3-degree radiation, maybe we understand that one. There's a lot we don't know. There's a lot we don't know.
Well, we're gonna learn that.
But we are
We're
gonna
trying,
learn it.
we're trying.
Yes, I mean, look at how far we've come in 100 years. And even 400
And
years.
we're just a little teeny speck, and look how
That-
civilized we are.
Yes, and our growth is asymptotic, I mean, our growth and our technology is growing that fast, And
Do
it
you
will
know
continue to.
Why they chose to orbit the sun?
It just,
It's a Lagrange point
yeah.
to where the gravity is like bouncing between the Earth and the Sun, so it takes very little energy to stay there. It kind of stays there by itself.
Do
Okay.
you have a website?
do I know? I'm on Facebook, Astronomy for Everyone with Ms. Galaxy. I am not going to be remaining in the valley after November, but I will be here for the summer, and I'll be doing a star party, well, we hope, we're trying to find a spot, through the Central Point Library at the end of this month. I'll also be doing another daytime talk there on Thursday, like the 26th or something. That's gonna be a really fun talk. Very different from this. I'm gonna do a lot of mythology because it's a broader audience. So I invite you to come to that. But if you are interested in having me do a presentation or bring my telescope to your little private dinner party or anything like that, I am available to do that. And I do have some cards, so you can get a hold of me like that. So
Are you going somewhere where it's darker?
I'm going to Mexico where it's warmer. And then I'm probably going to Bali. Yeah, yeah. So, any other questions?
There's, just came in today, new explosion
Oh,
in the
is-
Hercules.
oh,
Between that and.
astronomers are
Borealis.
expecting a new star to appear in the night sky anytime between now and September that has been years in, is it Betelgeuse? Let me just scan this real quick. It doesn't say. Oh, no, but it's gonna be in Corona Borealis, which
Yeah,
is,
Sean's watched it. He's taking measurements.
yeah, so
That's
it's.
supposed to- a lot of people watching it. It could be like any day now.
Yeah, oh, that's fun. So we might have a supernova right now.
Well, it'll be just a nova. It's not a supernova. It's be a nova.
Oh, a
It's a
nova.
recurring nova.
Okay, a nova is where one star sort of rips the material off of another star that's passing by, and in that process, it gets really big and bright, and there's a big exchange of material. It's that's called a nova, not a supernova. So, thank you for that. That's pretty exciting. I didn't know about that. I'm selling stuff for Mexico. Anybody else? Well, you guys have been so
Are you gonna-
attentive.
Are you gonna go see Teotihuacan in Mexico?
I don't know. I just live there when I'm there.
Yeah.
So I
Teotihuacan.
yeah.
epic.
Yeah, I know,
It-
I've heard,
It was the original
Yeah,
star.
right, the original
observatory.
observatory,
They used
yeah.
water pools everywhere.
Yeah,
So that they didn't have to stare at the sky, they could just make marks in the water
amazing.
with rods and stuff.
Well, I thank you all. If you are interested in learning more, come talk to me. And I really appreciate your attention. I hope that you learned something.